Mm-hmm.
The third one is going to start going into the organic analysis. It's going to go chemical analysis, and chemical analysis leading into instrumental analysis. And then the last one should be about medicinal chem.
Okay, okay. Thank you.
All right. How's it going, Salam? How's it going, Rashab? Uh, how's everyone going today?
Not bad.
Not bad. All right.
Yeah, good.
Just noting, I'm just gonna say this now. I am recording this, so if there's anything you guys are gonna say, it is recorded. So just be mindful of that. Recordings are all on YouTube if you want to see them later. I'm just gonna mute you down now. No hard feelings. Okay, I'll go. So just be mindful of that. So let me screen share. Let's see if there's anyone else joining before we begin. So we're mostly gonna be dealing with we're just gonna be dealing with the basics of diff. Tomorrow it should be the applications of diff, and then so we have let me actually check if the live stream is working. But today we're gonna be dealing with the basics of diff, right? Tomorrow we're gonna be dealing with the applications of diff. The day after that's gonna be integration and applications of integration. And then after that one should be the what's it called? Not what am I trying to say? It should be then going into like some further integration techniques and working through them, and that should be most of everything for diff. Because like calculus isn't a very big topic in methods, which is very good for us. So does anyone have any questions before we go into this? I got the two of you in one call. Rashab, you're not gonna say hi to Joe?
Wait, which one's Joe?
Okay, so let's get started. Let's get started with this one. So the first thing that we start dealing with is more or less just the form. Like it's some pretty basic stuff. We don't start off with anything crazy. But the first thing that we're just dealing with is just the idea of the average rate of change. So is anyone confused about how the average rate of change formula works? Essentially, it's just the gradient between 2 points on the curve. Yeah? Does anyone have any questions about that? You should already know this part, right? Is that all good? Can I get some thumbs up if that's all good? Right, if I ever like ask a question, just give me like thumbs up or thumbs down. It's all good, so I'm all good. For sure, yeah. Alright. All good. So here, right, I just want to make the distinction between the average rate of change and the instantaneous rate of change. Now you don't need to know these words like secant or chord, right? The idea is that the average rate of change is the rate of change at that point. Yeah. And I really want to focus this. I want to focus this now so that you guys understand this is the gradient at that point, or the other word, the derivative of the function, right? This is what we describe as the derivative of the function. The instantaneous rate of change is just another way of saying derivative. Yeah. And it's just at that point specifically. So does that make sense? Any questions about that? All this stuff you should already know from last year's. All good? Thumbs up, thumbs down, thumbs to the side, thumbs to the left, thumbs to the right. Alright, yeah. Oh yeah, Salam, you can don't worry about this one and tomorrow's one because it's just the same diff stuff.
Yeah, okay. See ya.
So I just wanted to show this one off for you guys. So I'm gonna turn this one off for the time being. I just wanted to show off this one. So I made this yesterday with the Desmos calculator. Essentially, right, the derivative helps us find the gradient of the tangent line at any point. So here, we'll talk about more on how to actually find these, yeah? But I just want you to understand that it's the gradient at that point, yeah? So it's the gradient here at a equals or at x equals 3. That's the point that we're looking at, yeah? So if we go back here, the tangent line is defined as a comma a, right? And that's the gradient of this tangent line is going to be that f dash of a, yeah? And we'll talk about more how to actually find the derivatives. Yeah, I really want to make sure this beginning part is like it makes sense to you, because you're going to be using all, the thing about this is it's very cumulative. Yeah, you need the stuff from before to do the stuff later. So any questions about that? Just give me like a thumbs down if there's no questions. Okay. There shouldn't be anything too crazy yet. So here, finding the average rate of change of this one, this isn't too bad. So we just use the average rate of change formula that we know. So here we have here A rock is equal to f of 4, take f of -1 over 4 take away -1, which is just going to be negative, so we're going to have here, so f of 4 is just -16 plus 8 plus 1, which is just -7. F of -1 is just -1 take 2 plus 1, which is just 2. So we just get here -7 take away 2 over 5, which means we just get here -9 over 5. Any questions about that one? So right now it's like nothing too crazy. Now we're going into the actual differentiating aspect. Now all of you should definitely know the power rule, right? I'm simply showing you this for completeness sake. Yeah? So the power rule, and more or less using the power. So here, these are just some of the properties of derivatives. So the derivative of the constant is 0, right? The derivative, if we have, let's just say f of x equals k g of x, that means the derivative of f dash of x is just k times by g dash of x, as well as the sum of functions to find the derivative of f dash of x is just g dash of x plus h dash of x. Like, these things you should already know from the previous, from last year, and I'm showing them to you for completeness sake. Yeah, so right now it's pretty boring, I know, you don't have to tell me. But is there any questions at all?
Wait, C is any number here.
Say again?
C is any number here.
Yeah. So like C could be like, like we could have here like 2, right? Which means the derivative of 2 is just 0. All good, Joe? You're kind of cutting out of it, that's all. Okay, perfect. Anything from you, Daniel, at all?
No.
Okay. So here, I'll ask for Sharp. What is the derivative of this function?
5x to the power of 4 minus 6x squared. Yeah, that's it.
That's it. Does anyone not understand that? I know I'm going through this stuff very, very quickly. Yeah. It's more or less because this stuff is very basic. Yeah. There's nothing too crazy about it. Because this is all year 11 stuff. So the same thing over here. I'll ask Daniel, can you tell me how I can find f dash of 1 by using the derivative of this function?
Well, using the formula, well, you first do the thing, and it becomes 20.
Remember,
Wait,
say
no.
f dash equals.
F dash equals to 9x squared minus 12x.
Yep.
And then we can just substitute 1 in, replace x with 1.
So we get here
And
9.
9 minus 12,
Which is just
just minus 3.
-3. Okay. So there's nothing too crazy about that. Here, they're just sort of phrasing it a different way. For the curve determined by the rule this, find the gradient of the tangent line to the curve at the point 1 comma negative 2. So here, I'll ask Joe, how can I find the gradient of the tangent line to the curve at the point 1 comma negative 2?
Derivative it. So 9x squared minus 12x, and then I sub in 1, 2,
So I go
and 1
here.
minus. Yeah. 9 so, minus 3.
Yeah, minus 3. So that's the gradient of this tangent line. Now, again, these are very, very basic skills. But the thing about the techniques later is that the techniques later that I'm going to show you are only worthwhile if you know this stuff, right? If you don't know it, it's a waste of time to know. Like, it's a waste of time. Yeah. So, all this is introducing is just the other notation. So we know that f dash of x and dy on dx mean the exact same thing. That's all this is saying here. Yeah. So here we could write here f of x equals x cubed, which means f dash of x equals 3x squared. Or alternative, we just do y equals x cubed, and hence we get this as our answer, which is basically the exact same thing. Any questions about that notation? Because you will have to switch between the two, or you have to understand both. Does it make sense for you, Rashab? Make sense for you, Daniel?
Yeah.
Okay. So here, using my understanding of the power rule, right? I'll ask. There you go. Using my understanding of the power rule, Rashab, how can I differentiate this one?
I guess. Would you expand it first?
Yeah, I have to expand it. So what's the expanded version?
X squared plus 6x plus 9.
Yeah.
Then the derivative is 2x plus 6.
Perfect. What about over here? Can I ask Joe? How would you find the derivative of this function?
What do I expand the whole thing first and then
Yep. So what's the expanded version of this?
4t? How to do the first one? 4t squared minus 2t
Is it 2t?
minus 14
Yep.
plus 1
Plus 1
times t plus 1.
plus t plus 2. Yep. Plus t. Yep. And then what do you do from there?
What? 4t. I'd rather do this on paper.
So you get 4t squared, take 4t plus 1, brackets, t plus 2.
4t to the power of
I have no
3.
idea. I have no idea what you're saying. You're like cutting out a lot. Like,
Oh, brother. 40 to the power of 3 plus 80 squared minus 40 squared minus 80 plus t plus 2.
so
That's 40.
take 4t plus t, take 8t squared, plus 8t squared, 8t squared plus 2. So that means we get here 4t cubed plus 4t squared, take 7t plus 2, which means what's the derivative of this one?
12t to the power of 2 plus 80 minus 7.
7. So Daniel, I'll ask you for this one over here. How would I differentiate this one?
Would I like simplify it?
Yep, so what's the simplified form?
So like I'd first factorize the top and like take out the x, making it x bracket, yeah, that. And then I could just cancel the x. which leaves me with x plus 3. And then once I dy dx it, I just get 1.
Yeah, so none of that's too bad, yeah? This stuff just repeats the exact same thing, yeah? It's just understanding here, this just means I'm differentiating in terms of x. I'm differentiating in terms of z. I'm differentiating in terms of z over here. So is there any questions about that? Yeah, what's up, Daniel?
Oh no, I misclicked.
Okay, okay. There's a misinput. So here, it says for each of the following curves, find the points, find the coordinates of the points on the curve at which the gradient of the tangent line at that point has the given value. So you have y equals x cubed, and we want the gradient to be 8, right? So Rashab, how would you do this one?
So first find the derivative.
Yep.
So y dy dx equals 3x squared.
Yep.
And then make that equal 8.
So you have 8 equals 3x squared, yeah?
Yeah, so then x squared equals 8 over 3. And then x equals root 8 over 3. Or plus or minus.
Yeah, good. Plus minus. Yeah. So then is that the final answer?
Nah, you need to sub it in to find the y value.
Yeah. So that's the big, like none of this stuff is too crazy. So we know here, if we put in plus the square root of 8 over 3, what do we get?
Um, 8 over 3 squared.
So we get the square root of, so if we plug that in for the x value, we get this whole thing cubed, correct?
Mhm.
If you want to simplify it, you can, but I'd accept that as the final answer. So 8 over 3, comma, right, here is just the square root of 8 over 3, all cubed. If they want a specific answer form, you can give it in that way, yeah?
Yeah.
But does that make sense?
Yeah.
If you wanted to give the other coordinate as well, you'd have to do a minus as well, yeah? So here you'd have minus root 8 over 3, comma, minus root 8 over 3 all cubed. Any questions about that?
No.
What about you, Joe and Daniel?
No.
No, okay. So again, like none of this stuff is too crazy difficult, right? It's these two questions here which may be a little bit new to you guys, yeah? So it says here, find the coordinate of the point on the with the equation y equals x squared takes 7x plus 8, at which the tangent line makes a 45-degree angle with the positive direction of the x-axis. So Daniel, can you tell me what we can actually do with that information in relation to diff?
Um. So, like, so we first of all we can find the derivative, right?
Yeah.
And that just gives us 2x minus 7.
Yeah.
And like from what I remember, using like the tangent, if we like do tan 45, you end up getting 1. And if we equate 2x minus 7 to 1, then 2x equals to 8 and x equals to 4.
Yeah. So, and then we can find the coordinate by substituting 4 back in here. Because we have the
Yeah.
formula m equals tan of theta, yeah? Right?
Mm-hmm.
Or, in this case, it'd be dy dx equals tan of theta, yeah? So, people tend to forget this formula. They're very forgetful when it comes to this formula. But does that make sense for everyone? Right? The big thing is that it needs to be measured in the positive direction. So here, right, this is the, like they measure it anti-clockwise, yeah? If they measure it in this direction down here, we have to find the obtuse angle over here, right? So we always measure it anti-clockwise. Now it says here y equals negative. So the tangent line is parallel to y equals negative 2x plus 6. Joe, what do you think I can do with that information? We know it's parallel, right? We know the tangent line is parallel to this line.
Loki forgot. It was something about like same or different gradient. I don't remember.
If they're parallel to each other, do they have the same gradient or do they have different gradients?
Same gradient.
They just have the same gradient. That's all that matters. Yeah? Because here we're not like looking for solutions. Does that make sense?
Yeah.
So here they have the same gradient. So that means here dy dx equals 2. So we have a 2x take away 7, which means that 2x equals 5. Hence, x equals 5 over 2. Does that make sense for everyone? Okay. Perfect. So, those are those skills that I've shown you, they're the key skills behind diff. And I'm going to make those assumed knowledge from now on. Yeah? So everything else, like everything in the future that I'm showing you, it's not assumed knowledge. But the stuff in the past that I've shown you, that's assumed. Yeah? So if we keep going forward, so it says here, if f dash of, so this is talking about the definition of strictly increasing and strictly decreasing. Yeah? If I have, let's just say, a parabola, yeah? You know, the line y equals x squared. Can someone tell me, where is this place strictly decreasing? I'll ask Rashad. When is this strictly decreasing?
Negative infinity to 0.
Strictly increasing.
Oh, increasing 0 to infinity.
Is the 0 inclusive or not inclusive?
Not inclusive.
It's inclusive. Yeah? This is partially wrong. Yeah? This definition that they've given, that's why I've said this up here. And I want to point that out. Strictly increasing is inclusive 0 to infinity here. Yeah? If we were given a curve that looks something like this, yeah? We're told that this point is like negative 2 comma 1. And this point over here is like 2 comma like negative 5. Yeah? Then, right? Let's just say we want to find when it's strictly decreasing. It's going to be between negative 2 and 2 inclusive. It's going to include those stationary points. Does that make sense? I want you to remember that for strictly increasing and decreasing, because they do ask this question. Yeah? I'll give you another example. Let's just say we have this curve, right? So this is what it looks like. So here it's going to be the line y equals 2x, and this is the line like, you know, y equals 2, yeah? And this point is 1. When is this function strictly increasing, Daniel?
Like from the place where it's like the gradient is more than 0.
So here, where's this one strictly increasing? It's not just more than 0. Remember, it can be equal to 0, because the stationary point of the gradient is equal to 0.
So from what?
So it starts here, 0, goes to 1, and then flattens out.
Oh, 0 to 2.
So that's y equals 2, yeah?
Yeah, wouldn't that be 0 to 2?
It's 0 to 1, yeah? This line is y equals 2x, yeah? So this is from x equals 1 to 0 to 1, yeah? It doesn't include this part, because really what the definition is that if I take a step forward, I will increase. But because this is completely flat, if I take a step forward, I won't increase it, yeah? But I won't decrease either. Does that make sense, Dan?
Yeah.
Does that make sense for for you two? You are? Okay. I want you to remember this definition for strictly increasing and strictly decreasing. So it includes stationary points, but it doesn't include flat sections. So here, right? This one's slightly different from the strictly increasing, strictly decreasing. It's asking me when the gradient is positive, yeah? So, or like when the gradient is positive, negative, or zero. So I'll throw this to Joe. Where do you think the gradient is greater than zero?
From like -197 to 56.
Say it again.
Oh, wait.
You're cutting out a lot.
Yeah. Let me think. Wait, is he talking about like straight? Is he talking about something different?
Okay. I'll just take because I can't hear what you're saying, Joe, because it's cutting out a lot.
Oh,
But here, right? It's talking about, well, like what are the x values such that f dash of x is greater than zero? That's what this is saying. Yeah. Here, the x values. This has to be between -1 and 5, not inclusive. Rishab, can you tell me what's not inclusive here?
Is it because it says more than 0?
Yeah. So that's where strictly increasing and strictly decreasing differ from the derivative is greater than or equal greater than 0, less than 0. It's like strictly increasing and decreasing is basically greater than or equal to 0. Does that make sense? So here, Rashad, can you tell me this one, right? Where's the derivative equal to 0?
At -7 and 5.
No?
Sorry, -1 and 5.
-1 and 5. Is that all chill?
Yeah.
So this is just restating the power rule, right? And how the power rule works for any non-zero integer. Yeah, so basically, right, if this is x to the power of 0, that means it's not, the power rule doesn't work here. Yeah. So anyway, we're going to apply that to negative powers. Yeah. So here, I'll let Daniel tell me what the derivative of this function is.
So f prime would just be 4x to the power of 3 plus 6x minus 4 minus, minus x to the power minus 2.
Yeah. So we just use the power rule like we always do. It doesn't change. It doesn't change whatsoever. We're using the same rule. It's just that we're using it for negative powers now. Yeah. So if we keep moving on here, yeah. What about here? Rashab, can you tell me what the derivative of this function is?
6x 6x plus 12x to the power of -3.
Perfect. Any questions about that? Again, this is not like I'm not like showing you hard stuff here. Yeah. This isn't like the big grid. I'm just making sure this, because this is again a class for completeness. Yeah. I don't want to skip over something because I think it's too menial, because that's very arrogant of me. Yeah. So keep going forward. Yeah. Joe, how would I do this one? Okay.
just
I still can't hear what you're saying, Joe. Rashab, how would I do this one?
So I guess I think you move like the x from the bottom to the top.
How can I do that?
X squared plus x to the power of -1.
Yep. So then what's the derivative of this function?
2x minus x. Yeah, 2x minus x to the power of -2.
So then here, how can I find the gradient of the tangent at this point?
Then sub in x equals 1.
Yep, so f dash of 1. And then what do we get as our output?
Uh,
We need 2, 1, take away 1 to the power of -2. How can we solve that?
Is it just 2?
No?
Oh, is it just 1?
So here, yeah, because it's 2 take away 1 over 1 squared, yeah?
Yeah.
Which is just 2 take away 1, yeah? Which is just 1.
Yeah.
Does that make sense for you, Daniel?
Yeah.
What about you, Joe? Perfect. I'll just let him. I'll let him join back. How have you guys been? How's the holiday started for you guys?
Pretty good.
Yeah, you got work up, don't you?
Yeah, I have to go at like 3:15.
Yeah, that's all. That's all good. Uh, we've gotten a decent amount of stuff done already. Like,
Yeah.
most of the stuff is pretty like it's like the same stuff you're used to. Yeah.
Yeah.
And like again, I'm just doing this because I want to make sure like I don't miss anything for anyone. Yeah, because if I miss stuff, then it's a waste of time.
Yeah.
So Joe's joined back. Okay. So I'll keep moving forward then. Here it says show that the derivative of f of all real numbers f of x equals x to the power of -3 is always negative. So here, how can I show that the derivative is always negative? What's the derivative of this function? I'll ask Rashad. What's the derivative of this function?
-3x to the power of -4.
Yeah. And then how can I show that this is always negative?
Make maybe make it less than 0.
Yeah, is there maybe an easy way for me to do this? To show that?
Sketch it.
Yeah, sketch it. So what should this graph look like? What should the approximate shape of this one look like?
Is it a truncus?
It's basically a truncus, yeah? So here we have an asymptote at y equals 0. We also have an asymptote at x equals 0. And here, right, this is what our truncus is going to look like. So then hence we can say f dash of x is less than 0. Does that make sense?
Yeah.
So you can sketch for sure. You can do sketches for sure. That it's not against the rules. But I'll keep going forward. So here with this one now, yeah, it says right. It wants me. This is me just graphing the derivative without having any rules. Yeah. So essentially, right, we're comparing these two graphs over here. So we're comparing this one with this one. This is the original. This is the derivative function. This is what the original function looks like. Its gradient there is going to be 0. So that's what the derivative shows. And here, if we draw a bunch of mini tangent lines, we see that the gradient is negative and it's getting smaller and smaller. Does that make sense for you, Daniel?
Could you explain it one more time?
So over here, right, we see at x equals a, the derivative is 0 because it's a stationary point. Yeah. So that's why here on the derivative graph, at x equals a, it equals 0. But then before that, what we see is that the derivative is negative, yeah, and it's getting smaller, yeah. So I'm writing a bunch of tangent lines. Do you see the gradient of these tangent lines is getting like flatter and flatter and flatter? It's getting smaller and smaller and smaller.
Yeah.
And then eventually it will produce this on the derivative. Now this side will then be produced if we draw a bunch of mini tangent lines. So do you see what I'm doing there? I'm using a bunch of mini tangent lines to approximate the shape. They don't want an exact value here. They don't want an exact answer here. They just want you to understand how you can sketch the derivative by just looking at the graph. Yeah? Does that make sense for you, Joe Rashad? Give me a thumbs up in the chat. Joe, can you hear me?
Wait. So since the gradient on the original graph, like on the left side of the original graph, is negative, it produces the negative part on the derivative graph.
Yes.
Does it not change like the shape of the gradients or whatever?
What do you mean?
Like because You know what? Never mind. That was a stupid question. I understand it now. Yeah.
So here, there is an assumption here that this is a quadratic. You do make a good point. There's an assumption here that this is a quadratic. Just make that assumption, yeah? Technically, this could be like a fourth power, a sixth power, and an eighth power graph, but that would just be unnecessarily complicated. So they'll only do quadratics if they're getting you to look at this, yeah? Or they'll tell you. They'll make sure they tell you. So does that clear up that issue, Joe? Maybe? Slightly? I don't know, man. Seems kind of sad. Okay, I'll keep moving forward. Let me just check something. Over here, I'm just checking if the recording is still on. I think the recording. I don't know, man. Yeah, the recording's still on. Okay. We'll keep working through this one. Yeah? So here, right? Do you guys see how between a, like when a is less than 0, the derivative is positive, right? When x is less than a, the derivative is positive. When c is when x is greater than c, the derivative is also going to be positive. Yeah. So that's what these two statements are saying to us. But between a and c, yeah. So when x is between a and c, we're going to have a negative derivative here. Yeah. And then over here at x equals c and x equals a, we're going to have zero gradients here. So how I'd sketch this graph then is, well, here I put as intercept, over here I put an intercept. It's negative, the gradient is negative over here, right? So I have this little curve, and it should go up over here because the gradient is positive on this side. And the gradient is also positive over here. Does that make sense for the three of you? Put just a thumbs up. Give me a thumbs up if that makes sense. Okay, perfect. That's good. So, keep moving on. So here, right, what would the derivative of this graph look like, Rashad?
So since it's all positive, it would also be all positive.
Yeah. So it would be will it be like this, or will it be a straight line, or will it be like? You know,
It'll be a straight line, I think. Yeah.
yeah, it would just be a straight line. So yeah, it'll be a straight line because it's a linear equation. It has a constant gradient, right? We can actually calculate the exact gradient here by doing y over 1. But we realize this is just y equals x, which means here, y equals x plus 1, which means here the gradient is just 1. Yeah? What about over here? What's the gradient of this graph?
The gradient is negative, so it'll be in the negative side.
Yeah. Does that make sense for the two of you? Yes. All right, Joe, I'll get you to do this one. Yeah? So here, tell me what the graph would look like before x equals negative 1. So before x equals negative 1, what does the graph look like to the left of x equals negative 1?
Like the derivative graph?
Yeah.
Or it's gonna have a negative gradient.
Negative gradient before?
Well, like from top left to bottom right, whatever that is.
So like here?
Yeah.
So yeah, it's going to look like that, yeah? What about between negative 1 and 1? What's it going to look like?
Oh, it's gonna increase.
So is it going to be like this?
Oh, it's gonna decrease to the bottom and then increase.
Yeah, so it's going to look something like this. So it's dotted line. And then what about past this point?
Increase.
Yeah, it's just going to be positive. Yeah? So does that make sense for you? Not Rashad, Joe?
Yeah.
Okay. What about this one? What would the gradient of this one look like? I'll ask Daniel this. What would the gradients of this one look like? of the derivative function of this graph?
Oh, well, it's positive.
It's positive, yeah? So here, will it intercept the x-axis at all?
Hmm. We'll do it once.
Yeah, it does say here point of zero gradient over here. So here, there's going to be a point of zero gradient, yeah?
Yeah.
So over here, right, is the graph going to look something like this, or is it going to look like this?
Option one.
Option one. What about on this side? Is it going to go up, or is it going to go down?
It's gonna go up.
Good, okay. So are you guys understanding the point of this? This one? Do you guys understand this? Okay. So I'll move on a little bit. I just wanted to discuss this one. Rashad, I'll give this one to you. Here it says draw a sketch of f dash where the graph of f is illustrated. Indicate where f dash is not defined. So here, right, what is the gradient of the part of the curve to the right, to the left of the x-axis?
Positive.
It's positive, yeah? And what happens when I get to this point here?
It becomes negative.
It becomes negative, yeah?
Yeah.
What is the endpoints
Undefined.
here?
0, 2, and 0, negative 2.
Inclusive.
So it's these two.
Yeah.
What was that, Joe?
No, nothing.
Okay. So here, right, it's not inclusive, yeah? There's a reason it's not inclusive. It's because we cannot differentiate at sharp points. We call this thing a cusp, technically, but I'm going to call it a sharp point. Essentially, if there's a bunch of jagged lines, we can't differentiate those, yeah? Because tell me what the gradient, the tangent line here would be, yeah? So simply, they're just not defined, yeah? At these 2 points, it's not defined. Does that make sense?
Yeah.
So here, I'll give you guys just a little activity. I want you to try and match these functions on this side to these functions on this side. Or what would you say is going to be the answers? Oh, what does answer option A go with?
Does it go with D?
D. Does everyone else agree with that? Thumbs up, thumbs down. Does everyone agree with that? Yes, no, maybe, kind of. Yes, so Daniel does, Rashad does as well. What about B? Which one does B go with?
F.
F.
What about C? Which one does C go with?
Is it E?
E?
B?
Did you say B?
Yeah.
Yeah, it goes with B. Yeah? What about D? Rashad, which one does D go with?
Um, D goes with.
No, D.
Yeah, D. Mhm. None of them.
D is a truncus, so you can think about it as like a 1 over x squared graph, yeah? It
Yeah.
goes with C, yeah?
Isn't the derivative decreasing?
So the derivative is decreasing over here, yeah? But it's
Yeah.
increasing over here.
Okay.
Does that make sense with C?
Yeah.
And what about E? Right, I'll give this one to Daniel. What graph does what is the which graph on this other side does E go with?
Um, hmm.
Which one?
A.
Yeah, it goes with A. Yeah, because here I can see that the derivative is basically zero. How's it drawn? It's basically zero over here, but over here it's also basically zero. Yeah, and then it goes through here, and it comes back. It comes back around like that. And then the last one, F. What's the derivative of F? You guys should be able to guess it. So it's the last one left.
E.
Yeah, it's just E. Any questions behind that? So now we're getting into the real stuff. So the chain rule, yeah? Basically, if we have a composite function, like a function inside a function, we can use the chain rule to differentiate. So here it is in both the function notation, or the Lagrange notation if you're feeling special, and the Leibniz notation. Yeah. So this is the Leibniz and this is the Lagrange notation. Yeah. They both mean the exact same thing. The Leibniz one is the one that shows up on your formulation, and I'll show you how to actually use it. Yeah. So if we go over here, right, it says y equals 4x cubed, take 5x, all to the power of -2. Yeah. Do you agree that this can be written in the form f of g of x, yeah? Where g of x here is equal to 4x cubed, take 5x, and f of x is equal to sorry, not that, x to the power of -2. Does that make sense?
Could you say that one more time?
So here we can write this function here like this as a composite function, where this composite function is g of x equals 4x cubed, take 5x, and f of x equals x to the power of -2. Yeah? Then we'll look back at this chain rule formula. I'm gonna just use this one here. The Leibniz one also works. Yeah? Right? Instead you just use y, use y and u. I'll show you both of them. But here, right, we'll find out what the derivative of x is first. What's the derivative of x for sharp? I'll ask you.
Negative. Oh wait, no, positive. Wait. Oh no, -2x to the power of -3.
Yep. And Joe, what's the derivative of g of x?
12x squared minus 5.
12x squared minus 5. Which means here, dy on dx of this one is equal to, again, if we look back at our chain rule, it is just going to be f dash of g of x, g dash of x. So here it's just going to be -2 brackets 12. Wait, my bad, gang. That's my fault. How do I erase so? Okay. Sorry, my bad. We get here -2 4x to the third power, take 5x, brackets 12, take away x squared, take 5. Yeah? And this one's to the power of -3. Does that make sense? What about you, Joe? What about you, Rashad? The other way you can do this is you can use use the Leibniz notation. I want you to get familiar with both of them. Yeah. So we can do u equals 4x cubed take 5x, right? Which means that y equals u to the power of -2. Here, right? We know that du on dx is equal to 12x squared, take 5. dy on du equals -2 u to the -3. Hence, right, dy on dx, again, by our formula, right, the Leibniz formula, equals dy on du times du on dx, which equals 2 u to the negative 3 brackets 12x squared, take 5. We can get rid of the u by substituting in that value for u. So we get negative 2, 4x cubed, take 5x, all take away 5 to the power of negative 3. Does that also make sense?
Wait, so if they give you f of x and not y, I'm not allowed to use like the u at all.
No. You're allowed to use both notations. You're allowed to use both. If they use f of x, you can use f of x. If they give you u, or if they give you y.
No, but like in my working out.
No, you can use f of x. I've used f of x in my working out.
No, like okay, so if they give you like f of x equals that, yeah, am I still allowed to use u equals 4x to the power of 3 minus 5x?
Yep.
All right then.
Yep, they mean the exact same thing. So here, if they said f of x equals x cubed, take away 5x, negative 2, they wouldn't care. It's the same thing for them. Does that make sense for all of you? So, here, right, it says find the gradient of the tangent to the curve with an equation y equals 16 brackets 3x squared plus 1. So how can I write this one in a form that I can differentiate using the chain rule? Because I haven't been taught how to differentiate this before.
Would it be something like 16 times 3x squared plus 1 to the power of minus 1?
So 16, 3x squared plus 1 to the power of negative 1. Is that what you said, Joe?
Yeah. Yeah,
Okay.
and you're missing the squared, but yeah.
My bad, gang. You right. So here, right? Oh, actually, I'll ask you, Joe. What would you let u equal to here?
I'd probably let u be what? 3x squared plus 1 would be equal to u.
Yeah. So then what does that turn y into?
16 u to the power minus 1.
Yep. So that means here, what is the derivative of u in terms of x?
What? Minus 16 u to the power minus 2.
So du on dx. So that's this one, not dy.
Wait, isn't that the u I just found? So, oh wait, yeah, I'm doing the inside, aren't I? 3x, yeah, 3. Oh wait, 6x.
6x. And then what's dy on du?
Minus 16 u power minus 2.
So minus 16 u to the power minus 2. Perfect. So Rashab, I'll get you to finish this one off. So our formula is dy on dx equals, sorry, my bad for the y's, equals dy on du times du on dx. So here, what is dy on dx?
6x times negative 16 u to the power of negative 2.
And then what are we going to do? Because we don't really care about the u.
Sub in 3x squared plus 1 is u.
Yeah, so here we can just turn this into negative 96x brackets 3x squared plus 1 to the power of negative 2. Is that all good?
Yeah.
Is that all good for you, Joe and Daniel? So we've just found the derivative. We haven't even finished the question. Right? So how can we then find the derivative? How can we find the gradient at this point? Daniel, tell me.
Let me just equate it to like 1. Let's substitute 1.
You substitute 1. So you get here negative 96 times by 1 brackets 3 1 squared plus 1 to the power of negative 2. How can you evaluate that?
Just get minus 96 and multiply. Is that 3 plus chat the thing outside the brackets? Go to right there.
That's negative 2.
Yeah. So that'll just be minus. Wait, not minus. 1/9.
So it's 1
Oh, my.
over 16, because it
Oh,
says
16,
3
16.
plus 1, which is 4, right?
Right,
And then
right,
we
right.
then have 4 to the power of -2, which is just 1 over 16. Yeah?
Uh,
So
yeah.
that means we just get here -6 is the answer.
Yeah, I get that.
Does that make sense for the two of you?
Yeah.
Perfect. So literally, I'm like just using new techniques and just expanding on the stuff I already know. Yeah. So here, right? It says, given that f dash of x equals the square root of x plus 4 and g of x equals x squared, find f dash of x where f of x equals f of g of x brackets. Yeah. So here, using our understanding of the chain rule, what is f dash of x, right? Remember that formula that we had? Rashab, what was the formula we had for this notation?
The f dash of x
G of x.
x dash of g of x times f dash of x times g dash of x.
So it's times g. So it's just this. So it's just f dash of x, g dash g of x, g dash of x. Yeah.
Yeah.
So if I go back over to here, right, this is it. Yeah. That's why I wanted to introduce you to both of them, because both of them are useful in their own different ways. Yeah. Does that make sense?
Mm-hmm.
So that means here, right, we know f dash of x, we do, well, f dash of x squared take away 1. What's the derivative of g? What's the derivative of g?
2x.
So that means we get here, that, Joe, finish it off first.
What would that be? Square root of 3 times x squared x squared minus 1 plus 4 times 2x, yeah.
Yeah, which is just the same
And
thing.
then
It's 2x square root 3x squared take 3 plus 4, which is just 1.
Alright.
Make sense?
Yeah.
Now, there aren't as many practice questions in this, but I'll tell you guys at the end of this where you guys can practice these skills after we've done them, yeah? And if you want, you can just send it to me or you can mark it yourself. I don't really know. Yeah? And the other thing is, you can find these on the formula sheet as well. Any formulas on the formula sheet. You will not. The only thing is, they only show off this Leibniz notation one. They don't show off this function notation one. So get used to get used to remembering that one, or at least internalizing it in some way. Does that make sense for everyone?
Mm-hmm.
How can I use the chain rule, right, to find the derivative of this function? Let's just say I do d on dx of this. Yeah? Very abstract. And they want me to find in terms of f of x and f dash of x. Do you want to have a go at this one, Daniel?
Okay, I'm not sure how to do this question.
So we'll think about it like this, yeah? Well, u will let u equal f of x, yeah? Which means that y equals u to the power of n, correct? Well, here,
Okay.
that means du on dx equals f dash of x, yeah? Because we can have this in terms of f dash of x. And dy on dx equals n u to the power of n take away 1, correct? Does that make sense for the two of you as well?
Yeah.
So that means here we have dy on du times du on dx, which is just going to be, right, n times by n u to the n take away 1, to the power of n take away 1, times by f dash of x, which is just going to be n brackets f of x square brackets n take away 1 times by f dash of x. Does that make sense to everyone?
Yeah. So still the same rule.
It's the same rule. I'm not like, I'm not interested. I'm not going to be like your teacher, which is like, oh yeah, shit, here's this formula. And here's a question that doesn't even need it, right? Type shit. I'm using the exact same stuff, yeah? So, here, for question 7, right? Who wants to have a go at this?
I think we shall have a go at it.
Oh, Rashad, bro. JW.
Alright,
So how
just find just make y equals 0.
So remember, we want to find when the gradient equals 0. Yeah.
Alright, so find the derivative.
So how can we put this in a more differentiable form?
Move the denominator to the top.
Yeah.
So
3x take away x squared to the power of -1.
yeah.
And
So
then
then chain rule.
So what is u equal?
3x minus x squared.
Yep. And what is u equal then?
U to the power of -1.
Yep. So then what is I'm just going to use y dash to represent dx, du and dx. Yeah.
Mhm.
So what is that?
3 minus 2x.
And what does y dash equal to represent dy on du?
-1, negative u to the power of -2.
Yep. So that means here, what does dy on dx equal?
3 minus 2x times negative u to the power of -2.
Yep. Which means overall, what do we get?
3 minus 2x times through 3x, negative 3x minus x squared to the power of -2.
Does that make sense?
Yeah.
And then how do we solve for when that's equal to 0?
Just make it equal 0.
Yep. So we do 0 equals 3 take away this times by negative 3x take away x squared to the power of -2. Yeah.
Mm-hmm.
So what do we do from here?
Null factor rule.
Yeah, null factor rule. So what can you get? So here 0 equals what?
3 minus 2x, or negative 3x minus x squared to the power of -2.
Not quite. Because here we have 0 equals negative 3x take away x squared to the -2. This doesn't have any solutions to it. Yeah. Right.
Okay.
Because think about it. If I square, like this is like me saying 0 to the power of -1 over 3x take away x squared to the squared. That doesn't have any solution to it.
Okay.
So then what does x equal to?
X is 3/2.
3/2. I'm just gonna say this now. These aren't hard questions, but the thing is, the other ones are just like a bunch of doing these sorts of things. Yeah.
Mhm.
So, any questions about that from anyone? Daniel, does that make sense?
Kind of understand it.
What part doesn't make sense?
The beginning part kind of confused me.
So like the y equals the 3x take away x squared to -1.
Yeah, I think I just forgot the main rule thing.
Yeah. So remember those index laws. Everyone always forgets them. Yeah.
Yeah.
So I'll ask you this, Daniel. How can I write down h dash of x of this function?
It's that sort of things. So wait. So if f prime of 4 gives us 8, then
So here, you use that formula that we have. Yeah. What does h dash of x equal?
is it the du one?
The first one. So it's g of x, g dash of x. Yeah.
Yeah. Whatever.
So then we can do h dash of 3, correct?
Yeah.
And we know that here we have f dash of g of 3, g dash of 3. We know here g of 3 is just 4, and we know that f dash of 4 is 8. So that means this whole thing is just going to turn to 8, correct?
Right.
And here, g dash of 3 is just 6. So this is 8 times 6, which is 48. Does that make sense for the two of you?
Yeah.
So that's why I've shown you both of those two
Yeah.
rules. They both have their own independent use to them. Yeah?
Wait, so did we not use G of free at all? Or
No, we're using g of 3. So
because
here,
there's only because we already have we already have 8 and we already have 6. So was it G of free equals 4 useless bit of info?
no.
Or am I stupid?
So here, right? F dash of g of 3, yeah? If I don't know what g of 3 is, I can't find f dash of g of 3, yeah? So they tell me
But
to substitute in f dash of 4, yeah? Because I know that g
oh
of 3 is
yeah.
the same as 4.
Yeah, I get it now.
So, okay. So this one here, again, the power rule, but here it's for for rational powers, yeah? So Rashab, can you tell me the derivative of this one?
Negative 2/5 x minus so we have negative 6/5.
Yeah? Plus?
It's 6/7 x minus 5/7.
Do you continue, Yerushal?
uh, Daniel, have a go at this one. So here, how can I turn this into something I can differentiate a bit nicer?
So is that like so when we like when we find the derivative, does it just like can we start off with like making it like x squared plus 2x bracket like to the power of 1/3?
Yeah. So perfect. We turn to the power of 1/3. Yeah. Then what do we use here? Yeah.
Can we use the first rule?
So we can use the first rule. What else can we use? What do we see here?
Um, dy over du.
Yeah. So it's a composite function as well. So here
Yeah.
we can say that u equals 1.
1/3.
No.
Mm.
So we have here y equals u to the power of 1/3. Yeah.
Oh,
And then u equals x squared plus 2x. Yeah?
oh yeah.
So that means.
So
Go on.
wait, no, continue.
So that means. I'm not going to use y dash. Y dash is stupid notation. So du on dx equals 2x plus 2. And dy on du is equal to u to the 3 to the power of negative 2/3, which means
Right.
that dy on dx equals 2x plus 2 brackets times it by u to the negative 2/3 over 3, which is just the same thing as 2x plus 2 brackets x squared plus 2x to the negative 2/3 all over 3. Does that make sense for the three of you?
Are
Yeah.
you wait? In most questions, are you allowed to keep like power of negative 2/3,
Yes.
or do you have to like?
Yes.
Oh, okay,
In most questions you can, yes. Absolutely.
all right.
But do you see there I'm like this is why I said diff is cumulative. You use everything you learnt in the past for everything moving forward. Yeah? It won't just be, oh yeah, this is chain rule, this is product rule. You'll have chain rule combined with product rule, combined with quotient rule, combined with all the other rules. Yeah? So, with these ones here, it says if y equals x plus the square root of x squared plus 1 all squared, show that dy on dx equals 2x over 2x x squared plus 1. So Joe, can you tell me how I can find the derivative of this function?
You have what? You would be x square root of x squared plus 1.
So you're saying that u equals x square root of x squared plus 1?
Yeah, and then you have u, and you get u dash, which is uh, what is that? 1 plus. How do I derivative x squared and square root of x squared plus 1 again?
So
Oh wait, power of wait, it's the power of 1 over 2.
yes, the power 1 over 2, yeah?
Yeah, so you get x squared plus 1 power of 1 over 2.
You're cutting out again, Joe.
Oh shit. Wait, am I still cutting out now?
Yeah.
Oh,
So I'll let Rashab try to do the rest of it. Yeah. So how can I find the derivative of this one, Rashab?
Turn it into x squared plus 1 to the 1/2.
Yeah. So here it's just x squared plus 1 to the 1/2. Yeah. And what's the derivative of that?
Chain rule.
Yeah. So here I'll show you a quicker way of doing the chain rule. Just find the derivative of the outside function. So the outside function here is the square. So what's the derivative of that one?
1/2 u to the power of negative 1/2.
Yeah, so x squared plus 1 to negative 1/2, and then go inwards, yeah?
Yeah.
So here, what's the derivative of the inside?
2x.
2x. So that means here, we get here, brackets, x squared plus 1 to the negative 1/2, yeah?
Mhm.
Negative 1/2 times 2x over 2. How can I simplify that?
Cancel the 2.
So we cancel out the 2's, and then we're left with 1 plus x squared plus 1 over negative 1 over 2 x, yeah?
Mhm.
And then from there, right, so we know that u equals u squared, which means that du on dx equal, dy on du equals 2u, yeah?
Yeah.
So here, right, that means we have dy on dx equals 2u times by 1 plus, brackets, 1 plus x over the square root of x squared plus 1. Yeah?
Yeah.
So this is where this one becomes a bit freaking annoying, right? Because now you have to try and simplify this whole thing. Yeah?
Yeah.
And got too much stuff in this one. Let me just quickly erase all this stuff. So we have here dy over dx equals 2u times by 1 plus x over the square root of x squared plus 1. Yeah?
Mhm.
So then we get here 2u times by, brackets, the square root of x squared plus 1 plus x over the square root of x squared plus 1. Yeah?
Mhm.
And if we remember, this x squared plus 1 plus x is actually the same thing as u. Yeah?
Yeah.
So that means we get here 2u squared over the square root of x squared plus 1. But we also remember that u squared is equal to y. So we get 2y over the square root of x squared plus 1. Does that make sense?
Yes.
You sure?
Yeah.
What about you, Joe? Does that make sense for you? What about you, Daniel? Okay. No? What's up? What's wrong, Daniel?
I don't know. This concept is okay, kind of going over my head.
Which one?
Like is it the chain rule that we just did? Oh,
So the chain rule. So u equals x plus the square root of x squared plus 1. Yeah? Y equals 2u. Yeah?
mm-hmm.
I mean, sorry, sorry. Y doesn't equal 2u. Y equals u squared. Yeah? So
Right.
here, du on dx equals 1 plus, and here we need to find the derivative of this one. Yeah? If we
Yeah.
do this thing called the quick chain rule, right? We just work from the outside function and we go in. Yeah? So here this is
Okay.
just going to be, so we times it by half. Yeah? And that's just x squared plus 1 to the negative half. So that's the derivative of the outside. Then we go inside and we times by the inside function, which is just 2x.
Right.
So we get here x brackets x squared plus 1 to the negative half, which is what? X brackets x squared plus 1 to the negative half is. Yeah?
Mm-hmm.
And then we know that dy on du equals 2u. Yeah?
Yeah.
Then we multiply those two together and do some algebraic manipulation to make them the same.
Okay.
Any questions about that? So here, you need to remember, I'm mixing the chain rule, the quotient rule, the purple. Yeah, what's up, Rashad?
I need to go now.
Oh yeah, all good, all good. Head on.
Alright, see ya.
Does that make sense for you, Joe?
That makes sense, yeah.
The big thing is going to be like going into the textbook and just practicing this stuff. Yeah. So, right. We'll try and do part C here. So how can I rewrite part C into something I can actually differentiate? Joe.
What? X squared plus 2x to the power of 1 over 5.
Yeah. And try
Uh,
and use the quick chain rule here to differentiate it. What do I do for that?
what? 1 over 5 times the x squared plus 2x. Yeah, what is that? Minus 4 over 5?
Yep.
Yeah. Yeah.
And then times by.
Wait, what?
So we
Oh,
times
wait. Times by 2x plus 2.
times by 2x plus 2. Yeah, so do you see how much easier that makes the chain rule?
Yeah, yeah.
What about this one?
Wait, I'm confused. I'm confused.
What?
Where did the minus 4 over 5 come from?
Because we take away 1 from the
Because,
power. Oh,
yeah.
So I'm finding, so you can think about it as I'm finding the derivative of the outside first, and then going inside to find the derivative of the inside. Yeah? So I'm just multiplying the derivatives to each other.
So we're still technically using the derivative formula.
Yeah,
You know.
Daniel.
Oh, okay.
So this is still the chain rule, it's just faster. Yeah?
Right.
So Daniel, how can you rewrite this one to something you can differentiate?
X squared minus 5x to the power of 1 over 3.
Yep. So what's the derivative of this one?
So 1 over 3 times x squared minus 5x multiplied by 2x minus 5.
Yep. So 1 over 3 times that. So this is the derivative. In fact, I can simplify that if I want to. Remember, this is negative 2 over 3. That's the only thing you missed.
All right, yeah.
So any
Okay.
questions from the two of you about that? Joe, Daniel?
I get it.
Okay. So now we're dealing with the derivative of e. Yeah. So this is the derivative of e to the x. Now I want you to remember both of these. This is the derivative of e. E is its own derivative. Yeah. This is the derivative of e to the power of kx. Yeah. These are starting to show up more and more on your formula sheet. Yeah. So here, tell me what the derivative. So here, the derivative of this one is 3e to the 3x. Yeah, Joe, tell me what the derivative of this one is.
Minus 2x wait, minus 2e to the power of minus 2x.
Yeah. So here, Daniel, how can I rewrite this one into something I can differentiate?
Minus 2e.
So e, not minus 2e.
Wait, e to the power of minus 2x.
Yep.
Equals to y. So then,
So plus e to the 3x, yeah?
and then when I dy dx it, I get minus 2e
Yep.
to the power of minus 2x.
Yep.
So,
Keep going.
and plus 3e to the power of 3x.
Yeah. So does that one make sense?
Yeah.
Does that one make sense for you to Joe? So here, another application of the chain rule. Yeah. In this case, instead we have the outside function is e, yeah, and then we're going up the exponential. So we can do it in two ways. So we can either do u equals 2x plus 1, which means y equals e to the u. Here, y dash or dy on du is equal to e to the u, and and u dash is equal to 2. So then we can say that dy on dx is just equal to e to the u times by 2. We replace the u and we get e to the 2 times e to the power of 2x plus 1. Does that make sense?
Yeah, that makes sense.
The other way we can do it is the quick chain rule. If we quick chain rule this one, well, first we have to find the derivative of e, which is itself. Then we go up and we multiply it by the derivative of the inside function, which is
2.
2. Yeah. So we get 2e to the 2x plus 1. Any questions about that? What about you, Daniel? Does that make sense? Wait, so you don't understand that? Wait, so you do understand it?
I do understand it.
Okay. Yeah. You're trying to trip me up. So here, try and quick chain rule this one, Daniel. Yeah? What's the derivative of e?
So okay. So the derivative of e. So using the du dx, dy dx, and then the dy du and the du dx rule, can it just like become e to the power of u?
So e to the power of u, so that's equal to y, yeah? Where then u is equal to?
So u is equal to wait, x squared.
Yeah, u is equal to x squared, yeah?
So then EU. So when I dy dx, I get EU times 2x.
So you get here, yeah, e to the u times by 2x, yeah?
So I finally get 2x e to the power of x squared.
Yep.
That my brain be working all the time.
So I'll let Joe have a go at this one. Try and use the quick chain rule to do this one, Joe. So what's the derivative of e?
So we got wait, hold on. 2x plus 4 times e to the power of x squared plus 4x.
Very good. Does that make sense? Daniel, have you got that?
Right.
He starts.
Could you explain?
So he just starts from the outside. He finds the derivative of e, which is itself. Then he goes to the inside function, and then multiplies it by the derivative of the inside function. So here, this is e multiplied by the derivative of the inside. So it's the fast chain, it's the quick chain.
Right. So like, would that mean that u is equal to 2? I mean, u is equal to x squared plus 4,
Yes.
and that means y is just equal to e to the power of x to the power of 2 plus.
No, so y is equal to e to the power b. Yeah.
Oh,
So
okay.
du on dx would then be equal to 2x plus 4 e to the u. Yeah?
Yeah.
Does that make sense?
Yeah, that makes sense.
Okay. So, I mean, we've already gone through this quick chain rule here. Yeah? And I won't worry too much about this because this is about finding the gradients of the tangent line, which we've done 100 times. Yeah? It's just differentiate it and then plug in the point. Does that make sense for both of you?
Wait, when do I make the derivative equal 0? Will it for stationary point?
We'll deal with that tomorrow.
Okay.
So that's tomorrow's one. We're dealing with the nature of stationary points. So any questions about that?
No.
Okay. So. Okay. Have a little go at this one. So, what is the derivative of this function? Any ideas from the two of you?
Do we use the chain rule?
Yeah. So what is u equal?
F of x,
And what is y equal?
e of u. I mean, e to the power of u.
Yeah. So what is dy on du?
Oh. Hmm.
F dash x.
E.
So
Right.
so that's what du on dx would be. Yeah. So it'd be f dash x. So
Yeah.
U times e to the power of u minus 1.
So it'd be e to the power of u. So remember, e is its own derivative.
Oh, wait, yeah.
Yeah.
E's tripping me out.
E will trip you out for a while. E is its own derivative. Yeah. So that means here, right? The derivative of this one, d on dx of e f of x, is just equal to f dash of x e to the f of x. Yeah? If we then substitute in x equals 2, we get f dash of 2 e to the f of 2. What's f of 2? Well, we're told it's 0. So we get here, and what's f dash of 2? That's just 4. So we get 4 times e to the 0, which is 4. Does that make sense for the two of you? What about you, Joe?
Let me process it for a second. So I'm just allowed to sub into like f of 2 as long as I have f dash 2. And then,
Yeah.
yeah. Okay.
So these are like abstract problems. You okay, Daniel?
Wait, I looked at it again and then I got confused. Wait, how do you get the e not like e to the power of 0 again?
Because it tells me that f of 2 equals 0. So f of 2, I'm just substituting 0.
Oh, so f of 2 equals to 0, which means yeah. Okay, I get it now.
Joe, do you want
Right.
to try to do the quick chain rule on this one? So what's the derivative of the outside function?
The outside function would be. Wait, shit, my brain's blanking. What? Yeah, my brain's actually blanking, bro. What the hell am I looking at? My brain's blanking. Yeah, no clue.
So here, the outside function is f, yeah? So the derivative of f is just f dash of x, right? The inside function is e, so we times it by e to the x. This is what I mean by inside and outside.
Oh yeah.
And then we can just substitute in two. So we get here f dash of e to the 2 times by e to the 2, which means you get 5 times e to the 2. Because we know that f dash of e to the 2 is just 5. Is that all good for the two of you? What about you, Daniel?
Um, yeah.
Okay. So these are a bunch more questions to practice it. I'm going to send you these ones. Yeah. I'm going to send you these slides, and I want you to have a go at going through them. Yeah. Because these use the exact same skills that we've been focusing on. It's just the chain rule and the derivative of e. Yeah. I'll have to find some more for these chain rule. But if you guys want to go back and retry these ones, be my guest. Absolutely. We'll just consolidate your understanding. So, the derivative of ln, right? The derivative of ln is just 1 over x, yeah? This is also on your, this one is on your formula sheet, actually. Does that make sense?
So k doesn't matter as long as it's over 0.
Yeah,
Okay.
so k doesn't matter. What about you, Daniel? Does that make sense for you?
Yeah.
So here, what's the derivative of this function?
1 over x.
1 over x. Now, we haven't been given something in this form. What can I use? What is my go-to best friend in differentiation? And it's not my data book.
I was about to say the data book.
Ah,
Trauma.
in methods. We've been using it. It's been computing.
Cas.
What?
My cas.
No,
Mm.
no. We can use the chain rule.
My power. Mm.
So, what am I letting u equal to here?
5 plus 3.
5x plus 3, yeah? What does y equal to then?
Log e of log natural of u.
Yeah. So what's the derivative of this?
5. 5.
And what's the derivative of e of ln?
1 over u. 1 over u.
So then here, what is my derivative for this function?
1 over 5x plus 3 times 5,
Yeah, so that means it's
which
just...
is, yeah, so 5 over 5x plus 3.
Does that make sense?
Yeah.
Yeah. So do you see how much the chain rule is just coming into everything? Yeah? The chain rule is your gospel. You want to learn how to do it fast, or you either want to learn how to do it. Yeah? Like here, they give you this generalized formula, but you can derive that using the chain rule. Yeah? Let u equal ax plus b, y equal ln of u, right? Here, y dash equals a. Wait, u dash equals a. Y dash equals 1 over u, right? Hence, dy on dx equals a over u, which is the same thing as a equals ax plus b. Does that make sense?
Could you explain that again?
So I'm using the chain rule. U equals this, y equals this. I'm using the derivatives of each one of these. So I know the derivative of this and the derivative of this one. Yeah? And then I'm using the chain rule. So I'm doing a times by 1 over u. Yeah? Which is just a over u. which is equal to a divided by ax plus b.
Oh, I understand it now.
Okay. I put the slide in twice apparently. So let's try and use the quick chain rule. What's the outside function here, Joe?
Outside would be log e u, and inside would be u equals x squared plus 2. And then we have u dash, which would be 2x, and outside, derivative of outside would be 1 over u, which is 1 over x squared plus 2.
So
Yeah, and then you times those together.
So we get here 2x over x squared plus 2. Does that make
Yeah.
sense?
Yeah.
Yeah. Daniel, what's your issue?
I don't know. I might be slow, but like, I don't get it.
So it's the chain rule. So y equals ln of u. U equals x squared plus 2. dy on du equals 1 over u. Du on dx equals 2x. Yeah?
Right.
I times them together, which is this whole bottom statement. Yeah?
Okay.
Because I know u equals x squared plus 2. Yeah? So I'm substituting that back in. And then I get this as my final answer.
Okay.
So have a go at this one. What's the outside function?
What's the outside function? Hmm. U equals to log ex.
That's not the
Is
that's
that
the
the
inside that's the inside function.
oh log equals to no log e x.
Nope.
Go ahead.
Nope. So the outside function here is just the square. Yeah?
Oh,
So here this one's 2 ln of x, and then we go into the inside function. So that's the derivative of the outside function. Yeah, I've just pulled this 2 out the front. Yeah?
right.
And then times that by 1 over x, which is the derivative of the inside function.
Mm-hmm.
Or if I want to use the chain, if I want to use the chain rule, right? We do here u squared, u equals ln of x, right?
Yeah.
And then I differentiate both and times them together, which is the same thing as this.
Okay.
Does that make sense?
Mostly. Yeah.
Like practice these ones after the class, like
Yeah. I would.
and like have a re-go at these ones. I'll make sure to send the slides out afterwards.
Right.
Okay. So this is why I find the quick chain rule absolutely integral. Yeah. First,
That's supposed to be a joke.
say it again.
Was that supposed to be a joke?
No.
Okay.
The jokes will be for later. Yeah. So, Joe, I'll ask you, what is the derivative of the ln part of this function?
1 over u,
So, which is 1 over
um, square root of x squared plus 1.
square root of x squared plus 1. Yeah. Then what's the derivative of
Yep.
the inside? Yeah. What's the derivative of the if we how can we rewrite this into a
All
full
right.
derivative?
So u would be equal to x squared plus 1 all to the power of half.
Yeah, x squared plus 1 all to the power of a half. Yeah. So here, what's
All
the
right.
how can we differentiate this half quickly?
Um, half times x squared plus 1 to the power of minus 1 over 2.
Minus 1 over 2. Yeah. And then what's the derivative
Yeah.
of the inside function?
2x. Yeah.
Does that make sense to you, Daniel? So it's the derivative of the outside, and we're going in to the next function on the inside, and we're going in further to the next function on the inside. That's why I don't
Wait.
really like showing the u equals y equals approach, because it only works for 2 variables. Yeah.
Yeah.
Okay. You're right.
Does that make sense, Daniel?
Like I was just saying that like the second part confused me again.
Times it all together. Just go deeper in and then times it all
Yeah. So
together.
because remember, this is a half. We times it by a half, and then we take away 1 from the power. This is the power rule. So I'm just using the power rule there to do this, to find this second part of the derivative.
Okay.
Yeah. And then I can simplify this. These 2's cancel out, right? I can see that this is actually the same as this. So I actually get 1 over x squared plus 1 x. That's what I get. I simplify this. Does that make sense
Okay.
to the 2 of you?
Come on. Need some more practice on this.
Yeah, I'll show you. I'll talk to you after this, and I'll explain where you can find some more questions for it. So here, right? I'll ask you, Daniel, what's the inside function? Oh, what's the outside function here?
Of that,
Yeah.
what you underline?
Yeah.
Um, hmm, log E.
Yeah, it's just the log e. Yeah. What's the derivative of the log e?
Um, is it 1 over U?
Yeah. So here, what is u in this case?
1 over log E?
So u is f of x. Yeah.
Oh,
U is the inside
right.
function. And then what's the derivative of f? What's the derivative of the next function inside?
S prime.
Yeah, f dash of x. So here, the derivative of this one is just this.
Okay.
So then, what is the derivative equal to when x equals 0?
What's the what?
What's the derivative equal to when x equals 0?
0?
No, I have here f dash of 0, f of 0.
Yeah, I'm lost again.
Well, f dash of 0, we're told it here. We're told f of 0 too.
So, 2.
Yeah, it's just 2.
I had tunnel vision again.
So, don't guess. Try and logic it out. Yeah?
Yeah.
Does this make sense to you, Joe?
Yeah.
I'll send you place. I'll tell you both places to like where you can find places to practice this one. This is I'm pretty sure how much. Oh yeah, we'll do quotient product and we'll do quotient and product. Will be this in here. I gotta remember how long this is again. Oh yeah, this goes to 80 slides. The last part of this is about continuity and differentiability. So, here, this is the derivative of psi of sines. Yeah? I can derive the same thing with the chain rule. Yeah? So here, for this one down here, I can derive this one using the chain rule. I can derive this one using the chain rule. This one using the chain rule is just, well, I let u equal k theta, yeah? Which means du on d theta is equal to k, right? So that means here, I just do, and then now I have sine of u. We know sine of u is just equal to cos of x. So that means here, the derivative of sine of u, which is just cos of u, times by k, right? Hence, the derivative of this one, f dash of theta, is equal to cos of u times k, which is just k cos of k theta. I just want to show you guys, the chain rule is literally everywhere. Like literally in every place that you'll look, yeah, there will be an application of the chain rule, the diff. Does that make sense for two of you?
Can you repeat the last thing you said? On my end, it kind of cut out.
The chain rule is everywhere.
Okay.
So the same thing we can do for cos, but this is a derivative of cos. Now, I'll tell you this to both of you now. You don't need to memorize any of these derivatives. They're all in your formula sheet. I like how no one looked at the calculus section of their formula sheet to do these questions. Place a lot of trust in me. But you don't need to memorize these. Yeah, they're on your formula sheet if you need them. You just need to know how to use them. That's why I tell people to learn how to use the chain rule. Yeah. So now, for a little bit of notation's sake, you guys won't know this. I know this because Spesh kids are taught this. Well, sec of theta is the same thing as 1 over cos. And the reason we need this is because the derivative of tan is equal to sec squared theta, which is just equal to cos squared k theta. Does that make sense?
I heard we don't use sec at all in
Yeah.
methods, and yeah, just use the cosine squared.
So if I pull up the methods formula sheet here, I'll just show it to you. In the formula sheet, they have both. Yeah? So VCAR accepts both, right? But I'm going to tell you guys to use this one because neither of you do spec. Yeah? I'm going to tell you to use the cosine one because the sec one's a bit special. Does that make sense? And here, this is all the derivatives. Yeah? So you don't need to memorize any of these. Does that make sense? Hello?
Yeah.
You sound lost, Daniel.
I'll look it out.
Oh, I'll talk to you more. I'll talk to you more at the end of this. Just we'll keep going for now. So here, right? What's the outside function here, Joe?
Outside function would be sine. Wait, cosine u, cosine 2u.
Yeah. So
Wait, cosine u, cosine u.
So it'd be cosine u times by the derivative of the inside.
Two.
So that means here it's just going to be 2 cosine of 2 theta. Yeah.
Yes.
Yeah.
Yeah.
Does that make sense to you, Daniel?
Not really. You said are you talking about the inside function or the outside function?
This is the derivative of the whole function.
Both.
This is the derivative of the whole function. So
Okay.
I use the inside function and the outside function to find the derivative of the whole function. Yeah?
And what was the first thing you wrote down?
So this is cosine u, yeah? Which is just the derivative of sine.
Right.
And here, times that by 2. Realistically, I just want you to keep this as cosine of 2 theta, yeah?
Yeah.
We even defined u, so we can't use u, yeah? But this is
So why are we
cosine of 2
multiplying?
theta. Because here we're timesing by the derivative of the inside function.
Right. Okay.
So the outside function times by the derivative of the inside function, yeah? Here, what's the derivative of the outside function of this one, Daniel?
But that's the secant one.
Don't use secant.
Oh. In that case. 1 over cos.
Yeah, 1 over cos squared 3 theta, yeah?
Yeah.
What's the derivative of the inside function?
We're multiplying it by 3, right?
3. So that means it's just going to be 3 cosine squared 3 theta. Does that make sense?
Yeah.
Does that make sense for you, Joe?
Yeah.
Are you picking up on like how like the chain rule is just applying to everything?
Yes, but I'm so lazy. I don't want to remember the whole thing right now.
Don't worry. I'll send you guys some practice for this a bit. For this one here, what do you guys think the outside function is? Because sine squared of 2 theta is a special notation. Most trips people's up.
It shouldn't be cosine squared u, right? Shouldn't.
Here,
Would it be? Would it be like two cosine u?
so this here, sine is the outside function. So squared is the outside function. They write it like this for notation's sake, but it's actually meaning this. Yeah.
So
Here,
two cosine u.
so no, it's 2 sine of 2
What?
theta. So that's the derivative of the inside. Yeah. I mean the derivative of the outside. Then we go inside.
Oh wait, so we're doing double layer again. Okay.
Yeah. Then we times by the derivative of the inside. Yeah. Which is just 2.
2.
So we get here 4 sine of 2 theta cos of 2 theta. Does that make sense, Daniel?
Yeah.
Yeah, that does.
Like looking at those formulas, it does.
Say it again.
Like me using the formulas, yeah, it does.
Yeah, like using the formulas it does, but we need a faster way of doing it, especially for this sort of question. Just because a double layer thing, like it'll take you like 5 minutes when it should only take you like 1 or 2. I'm gonna say this now. Diff isn't like a particularly focused upon it's a focused upon topic, but it's like it's focused upon in the sense of it's applied to other units. So in your SAC, you won't see it. You will see a diff question by itself, but in the exam you won't. Yeah.
Are we
Right.
doing anti-diff this week?
Yes.
Okay.
Anti-diff is a little bit more straightforward because there's less application for it.
Yeah, but I hate anti-diff, so we'll see.
Okay. But does that make sense for the two of you?
Yeah.
Yeah.
So what about this one? I'll ask Joe. Joe, what do you think how can I start differentiating this one?
Let's see. The outermost function would be two, like derivative of the outermost would be 2 sine 2 theta plus 1
Yeah.
times cosine 2 theta plus 1 times 2.
Yeah. Does that make sense?
Yeah.
What about you, Daniel? Does that make sense to you?
No.
No, what part?
So two sine, yeah.
Say it again?
Wait, hold on. I'm kind of beginning to get it. So you know how it said it says sine squared.
Yeah.
So it just becomes 2 sine and then blah blah blah.
Yeah.
Okay, I'm beginning to get that.
So there's we'll keep going on with this stuff tomorrow. Yeah. Because we just keep going we keep going through the trig stuff, and then eventually we get to the quotient rule. Yeah.
Yeah.
But most of everything is the chain rule. Yeah. Most of everything is can you chain rule real good. Yeah.
What? And then tomorrow we're gonna do what? Quotient and product fused with the chain rule.
Yeah, quotient and product fused with the chain rule,
Uh,
as well as continuity, limits, and differentiability.
oh yeah. About classes, is it still running normally, or does it only run normally after you finish like this week?
So it's running normally as well. Yeah.
Okay.
Yeah, low key in the
So I still wait. So do I still have class on Thursday or?
Yeah.
Okay.